Okay, good morning, everyone. The numbers online and here are growing, but we'll start on time so that people could, we can just benefit from the time. We're not limited. We don't need to leave at 10:30, but just to benefit from the good morning of this day. So today we have the third quantum technology business seminar. Just a reminder, this was an outcome of one of the workshops Carleton University and Sprott School of Business organized in February, when we decided that it's good to have such type of a forum for people interested to learn more. Basically, using the wisdom of people in the domain for people that are interested to know more about the domain. And the overall opinion of the people in the business is that adoption of quantum technologies will depend on people who are not necessarily domain experts. They will run their businesses, organizations, manage their people. So they need to be aware of what quantum is able to, even though they may not be the one developing, the one that are dealing with the hardware. So today's speaker, Khaled, he's one of the ideologists behind this seminar. And it's so nice to have people like him because he's already a welcome speaker on so many topics. He already opened the seminar with some of the foundational concepts on the first seminar. The second seminar, we had a little bit more business-oriented team. Now we're back to a little bit more technical topic about the Qubit technologies, which again refer to the main concept. So it's a nice way to look at quantum from the fundamental unit of quantum computing and other quantum technologies, and go back again to the main concepts and so on. But I believe that this is really the source of any understanding of what quantum is, and Khaled has been spending many years working in this domain. He's a senior research staff at NRC, dealing with the quantum publication and quantum technologies group. We had a fundamental relationship with the National Research Council of Canada. Today we have stronger representation. We have Dr. Patel Kutsol from the Canadian Photonics Publication Center. He's one of the adjunct professors with the Technology Innovation Program at Carleton. So they work closely with Khaled, and there'll be more people coming later on. So without further ado, I'll just invite Khaled, and he could tell us again about his group a little bit and then get into the issue. Thank you. Thanks.
Thank you very much, Stoyan, for the intro. First of all, I want to apologize. My voice is a little hoarse. It's allergy season. So, yeah, welcome to allergy season. Anyways, I want to thank you all for coming out. And this is the second talk or third in the seminar in this. And really, it's continuing what I talked about in the first talk about quantum foundations. But I want to extend it more towards the technology. So the first talk was more about the science. This is more about the engineering. But I'm going to do a bit of a refresher just to get us in the mood for quantum, and then start talking about the actual technologies that are out there and what's needed. And a few surprising facts about quantum that I'll get into as well. So my talk here is Qubit Technologies. You see the Cheshire cat, sort of a representation of cats. Cats and quantum are somehow bonded. Schrodinger's cat, this Cheshire cat, and how the Cheshire cat kind of disappears except the smile stays. And actually, there's a paper out about quantum, the quantum experiment that had a photon, but its spin or its polarization stayed and the photon disappeared. So it's like a Cheshire cat type thing. So it's a very strange world we live in terms of down there in the atomic physics. But the whole point of the quantum engineering is to take that strangeness and bring it up so we can use it for maybe hacking into the computer of the universe and solving cancer questions and things like that. So there's a real serious business in terms of how do we exploit this technology. So the contents of my talk really is to talk about starting off with, again, Schrodinger's cat. Is it alive? Is it dead? We don't know until we open up the box type of thing. We talked about last time, but what is a qubit? How do they differ from classical qubits? What are the challenges in building stable and scalable quantum systems? Huge challenge. Just a bit note, when computers were actually coming, online back in the 40s and 50s and all that kind of stuff, very famous mathematician John von Neumann was very concerned about noise in the systems. But if you look at semiconductor systems now, when traditional transistors, they're very good. So his theory was really not needed. But now his theory is actually very, very needed in terms of solving the noise issue with quantum systems. And then after we talk about generally what a qubit is from a ideological perspective, how do we realize and manifest these qubits? So I call these qubit modalities. What kind of physical form do they take? And then quantum engineering. So for 100 years, we've been doing quantum science. Now we're in the era of quantum engineering. How do we turn the science into something that actually can be used? And then the opportunities, right? Because now we've turned into an engineering phase. The engineering phase and the business phase have always been across all technologies married together very much. We need the resources in terms of the funding, in terms of everything else to actually realize these things. So back to what is a qubit? Okay, so imagine you and your friend are out in the garden and you're holding a garden hose very taut, right? Very tight. And then your friend sends over a hill over to you. And then you send over a valley to your friend. Now you guys do this at the same time. What happens? Great one. Any other thoughts? I like this to be interactive. They cancel each other out. So this picture looks exactly like the first picture, right? But that's a moment caught in time. That is a qubit. Because once the next second happens, they come back out. The hill and the valley come back out. So it's important to know that this is a qubit. But we can't hold on to it too long because the next moment's gone. So the whole point of quantum technology is hold on to this moment as long as you can and do something with that moment. And now you've got access to two things at the same time. And that's where your computational power comes from. It comes from efficiency, being able to do many, many things at the same time. And we call that readout. Once you're done, you read it out. You let that moment happen and you see what happens. Now, in the last talk, I gave this little lecture on what a Mach Zehnder is, okay? And essentially, I talked about what's important about it and what kind of links are needed to make sure that you have a certain condition, okay? And so you can refer to that talk and how I introduced it, but I want to start from here. And if you turn on a laser, if that spatial condition is met, you will always get a detection at detector 2 and always a nothing at detector 1, okay? This is actually, you can do it, but it's very hard to implement. Why? Because you're playing with phases of the light. You're making sure the phases of the light line up just right so that you always get nothing at detector 1 and always something at detector 1 and always something at detector 2. So it's possible, but it's not easy. If that condition is not met, well, then you're going to get 50-50. Okay. Now we switch to a single photon picture. So the single photon is believed to be a quantum picture of reality. You have a single photon. So if we let a single photon out, when it gets to the final beam splitter, we'll see because it's following the same type of condition that the laser is doing, you're going to get an output that's always going to go to D2. If it takes the other path, it's always going to go to D2. So it's following the same type of thing that the normal laser would do, okay? Now, there's a test, there was 1993, I talked about this last time, the Vadman bomb tester, where you want to see if there's a bomb in the other arm, and it's photosensitive, right? So if you have a photon that comes that takes the wrong arm, well, it either explodes or it's a dud. Okay, there goes your setup. Now the photon takes the other path. Now we see the photon did not go in the other arm. It went to another path. Now, is it going to go into D2? Because it should. That bomb it's not aware, it should not be aware of that bomb. But it goes into D1. So what that actually says is that there's some real counterfactuals that are being accessed. So when you hear about quantum computing looking at everything, it sounds kind of hypey and sounds kind of like whatever, but there is something real there. Okay, it's looking at different paths, and these paths add up in phase. There's something called the quantum wave function. So for this experiment, which has actually been tested already by Bob Boyd at the University of Ottawa, there's something that's adding up, and this is really the essence of quantum computing: gaining access to other paths, gaining access to other counterfactuals, so you can do something with it. Okay. Now we take the system. Now, okay, the details of quantum computing and all that kind of stuff, they're really, really details. Like there are a lot of really hard details to follow. So I'm not going to get into that. This is sort of a broad view. What I'm going to try to do is try to explain it using this situation where you have access to counterfactuals. Okay. So if we say that this is the quantum system we're interested in, one of the outputs is the traditional classical output that we have. Now, instead of a single photon, what we do is we take a whole bunch of qubits, superpositions, and input them into the system. Okay? So that instead of a single photon state, we input superposition of states. And now your bomb is this algorithm or pattern that you have in the system that you put in a particular place in the system, whether it's a Shor algorithm, Grover algorithm. I'm really making this very general, okay? So you're putting it in a path of the system where it's counterfactually accessed. And so when you do that and you use the phases of the system, you end up getting the answer a lot faster than you would through classical fields. So the quantum output, you get the right answer in 10 days instead of 10 to the 80 days. So quantum really isn't doing something magical. It's just getting to the answer faster. Okay, so we're talking about efficiency, where in computer science you would call P versus NP, right? Maybe we're getting to an axis of P. So there's questions even in computer science where Shor's algorithm was actually surprised that you can get certain things in polynomial time versus what was thought to be exponential time. So what you have here in classical computing is you have a beginning and you have an end. That's the goal you want to get to. But in quantum, what happens is all paths are searched simultaneously. However, you don't have access to these. You only have access to one answer, right? However, that's the whole point of measurement. So if you make a measurement, you collapse things. But before you make that measurement, there are things that you can do without actually measuring it that manipulate those paths. So you can favor one path over another by giving it a different phase and adding it up. So the interference is you want to make a system where you amplify what you changed in phase and then deconstruct what you don't want to come out.
Can you linger on that for a moment?
Sure.
The concept of deconstructed that you don't want to come out.
Yeah.
So I think that's key to understand the start and goal.
Absolutely. So when we think of classical computing, usually we think of, okay, give me the answer. Here's the question, give me the answer. Quantum computing is a little different. I have an idea of what the answer is. So this is why in classical computing, I can separate the hardware from the software easily. I can make the hardware, it's going to be on and off Boolean logic, and then I come together with my software and I tell the Boolean logic this. But it's a serial application. With quantum, hardware and software are very married. They're very together. So when you make a quantum computer, you're basically shaping it to solve a particular algorithm. You're looking at Shor's algorithm. So you have an idea of what you need to be done. And you encode what needs to be done through phase relationships. And because you have phase, because we talked about if you're a hill and a valley, you cancel each other out. Those are null, they become destructive. They don't add to the answer.
Okay.
And if you know what you are looking for, they add constructively. And therefore it builds up the amplitude. Then when you make the measurement, you get the answer that you do.
Of the accuracy.
Yes, exactly.
So that construction is effectively reducing the noise, as it were, of the incorrect input.
Noise in the algorithmic part. There's real noise, and then there's this noise that the stuff you don't want, right? The wrong answer.
But you're trying to minimize the inaccurate inputs. Would that be a reasonable way of describing it?
Yeah, you're kind of minimize. Again, you kind of know what you're looking for
Yeah.
in a sense.
Within this balance of cancellation.
Yes, exactly. Actually, the next slide's kind of make this a little bit clear. So there's your multiple possible histories that you generate from the path in the system. And the computation explores many trajectories, but that's in the second configuration space, and it's not something it's hard to access. What you end up doing is you start to add the information you're looking for through phase. So phase causes deconstructive and constructive interference. And then what happens is when you make the measurement, the probability concentrates on the right answer. And that's what gets you to speed up. We're talking about speed up. We're not talking about an oracle, tell me the answer to whatever the universe. We're talking about a particular system, and we want this to be sped up. Because ultimately, if you look at Shor's algorithm, we want to decrypt codes. We want to break encryption. We need to factor this incredibly large 10 to whatever digit composite number into its primes. That's the goal. So you build that into your system through phases, and then that's what comes up. So we do not read out these histories. We only get one measurement. So the power comes from engineering interference that only useful histories survive. Okay, and this is why I was saying that computer science, hardware, they're tied at the hip, unlike classical computation. So there has to be a strong relationship with the algorithm people and the hardware people. So qubit versus bit. So in the old days, if everybody electrical engineer, this is the NOT gate. It's, everyone's used to that kind of stuff, the ANDs, the ORs, and all that kind of stuff. And in quantum, you've got different types of gates. Because now you're operating on like that superposition of hill and valley, and you're trying to manipulate it. And so you can switch the hills and valleys, you can control the phase of the valley. And then you can do an entanglement operation with the help of different qubits. So in the system, these operators would be manifested in terms of these splitters, mirrors, and the bomb, I guess, is what the actual algorithm is. Now here's the problem. Because quantum information is so fragile, you've got this fragile thing that's superposition on top of each other. If you blow on it, it's going to ruin it. So noise is a very big problem in quantum systems. Okay. And one of the first ways of trying to tackle this is trying to make many, many copies of what you're doing. So that if one goes away, you have that same kind of like voting type situation. If one bit is flipped and not the others, then okay, well, I think I'm something. So the point here is to make many, many. The problem when you come to realize these systems is that it physically gets larger and larger and larger to the point where it's like, I need a football field size quantum computer to solve a problem. Because when I'm looking to solve a particular problem like an RSA problem, decoding a huge number into its primes, I need a lot of logical qubits. These are qubits that describe the system, but that translates to many orders of magnitude of physical qubits. So that's a huge problem that people are working on right now. Oops. I was supposed to surround this picture with FPGAs, but I'll just go to here. So if you imagine your qubit as a teeter-totter, okay, this is where classical technologies have become very, very important. Okay? Where your transistors now can surround your qubits and do the corrections that are needed. So in systems, for example, that are non-electronic, like photonic systems or things like that, they need other ways of protecting their information. But if you can surround it by classical technology, then you can start to correct these problems. Just like, for example, if you have a situation where you have your FPGAs and they sort of read out and do constant measurements of the system and adjust accordingly. Okay, that itself is a bit of a problem. But again, it really relies on electronic technology getting better and better and better. Think of it as like, Elon Musk's landing the rocket back on its post, right? The control systems are unbelievable. So the same thing in quantum systems, electronic traditional control systems are going to be very critical to them. in some companies, when their qubit is an actual solid state qubit, it can be surrounded by transistors. So that's a key towards fighting this battle. And there's other ways of people implementing fault tolerance. Oh, okay, there it is. I got it messed up my slides. Anyways, you can surround your qubit with FPGAs. And even FPGAs are kind of getting to the point where they're too slow. We need to switch to actual ASICs. I was at Nortel many, many moons ago, and that's when I worked on ASICs, application-specific integrated circuits that are geared towards control systems for quantum. I guess I doubled my slides. There you go. Anyways. Okay, now we come to qubit modalities. And now we talked about what a qubit is, why it's different than a classical bit, what does it mean, and how do we try to manipulate it. But now we want to realize these things in physical systems. So, different qubit modalities will take different shapes. So, for example, NRC, we're working on semiconductor spin qubits, and we're also working on photonic qubits, where the form, for example, is, a missing electron, which is called a hole, right? And it has quantum attributes like spin, charge, and that kind of stuff. And we can manipulate it, have it hold that state of up and down at the same time, just like the Hill Valley in the roll. You can hold that state for a long time and start to manipulate it without actually observing what state it's in. Because once you try to observe what state it's in, you collapse the state. Okay, and then we've got systems and the different material systems, for example, strained germanium that we can work in. And then also indium phosphide for the photonic qubit stuff. We have nanowires that can hold something called an exciton, which is really something that's going to become a photon. But that state is sort of still has a quantum state. And then once you make the measurement, you get your single photon. Or the photon actually collapses, the exciton collapses and takes that quantum information into the photon. So what's strong about a photonic qubit is that people call it a flying qubit. So if we're talking about distributed systems, eventually what's going to happen is no matter what kind of qubit you have here and what kind of qubit you have here, you need to connect them over a network. And the flying qubit is the photon. So eventually you need to transduce quantum transduction from your stationary qubit, whether it's a superconducting qubit or spin qubit, to a photonic qubit eventually, and then back. Okay, that's distributed quantum computing, right? Architecture. Okay, speaking about modalities, one of the famous ones is the superconducting modality, which is the transmon. So really, it's just an oscillator circuit that has something called a Josephson junction. If you're interested, you can read about it. It's a way of creating basically the qubit itself is which way is the current going around the circuit. That itself could be going this way or this way. And that's the hill and valley that we're talking. Okay, and then you have your readout stuff to choose, what direction it's going. And each qubit is going to have its own modality. It's going to have its own strengths, right? It can hold this for microseconds for that state and things like that. How well does it, and also how well does it uphold to noise? How badly does noise affect it? And we've got companies already here in Canada. We have Enyon, and we have other companies that are in this space, trying to do their best to get to the many logical qubits that can be used for RSA breaking. So essentially, you're creating the spectrum, and the spectrum itself is the quantum steps that you take, that you encode information. Another modality is trapped ion. So back to the superconducting. This is really the one that's mostly out there, and it's really leading the race when it comes to quantum computing. Okay. Then you have another type of modality, which is trapped ions. So the trapped ions actually comes from clocks, cesium clocks, that type of technology where you can hold an ion and then you start manipulating its states using lasers. So the laser will encode some information, and then you can start to manipulate those states using the lasers. And then you can read out the state through a measurement. And again, each qubit is going to have its strengths and it's going to have its weaknesses. So for example, if I want to have quantum information tied into my clocks, somehow timing is very important. Military loves the timing. Timing is important. I need to do something with timing, and I need to do something quantum with timing. Well, ion traps look like they're the best that you can play with. But then I want to do some computing with it. So not so much actually people want to do quantum computing ion traps, but then you could transfer that information to a trained one, what we talked about before, the superconducting qubit. So companies in this space are leading in realizing the qubit technology for trapped ions. And again, they're going to have different types of coherences. How long can I hold that valley hill rope for a long time? That really depends. Another type of qubit is the neutral atom qubit. Okay, so neutral atoms are essentially neutral atoms, but they're held at a very cold temperature. Okay, and what they bring actually is that you want to do quantum computing with them, but they have the aspect of bringing in gravity and mass inside the calculation as well, because they actually have mass, and you can turn them into a superposition of state. So a bunch of atoms can sort of become one quantum state, and therefore you could do like actually back Anton Zeilinger was got the Nobel Prize in quantum engineering entanglement. When he first started in the field, he actually measured the gravitational constant using the quantum wave function. So when you have particles that have mass that can be put into quantum states, you have access to talk about gravity, and that could be useful for sensing, using gravity sensing. And so companies like this, there's companies here that are working in this space, and making a lot of headway in this. And again, it comes back to what are your coherence times. So here, for example, the others were in milliseconds. Here you're at hundreds of seconds, okay, because you're at a very cold temperature. That's a long time, and hundreds of seconds is very long. And then instead of dealing with stationary qubits, just deal with the flying qubits the whole time, right? Make your quantum computer just deal with photons and use those as the actual qubits. So that's actually a very strong point why photonic qubits are important. These companies are leading the way in terms of photonic qubits. But again, what happens is, these systems, while they're good in flying qubits, things like that, perhaps they're harder to deal with for fault tolerance, right? So the other modality is better in dealing with fault tolerance. Because if you can't deal with fault tolerance, how nice your system is, it's just, you're not going to have a quantum computer. And one of the systems we're working on in quantum dots is it's actually very, it lends itself well to fault tolerance because you can integrate these dots with actual transistors and actually correct them live. Okay, so it's easier to get access to fault tolerance. And so these are companies that obviously Intel is very interested in. They make transistors, and therefore it's good to surround their qubits with transistors. They can do that. And so at NRC, we're also interested in. I'm working with Sergey to get this going. And then finally, there's many types of qubits, but finally on this list here is the spin defect qubits. We have a crystal that one of its lattice points is a different type of atom or a vacancy or whatever, and that acts like a qubit. And then for these qubits, yes, you can try to do some quantum computing with them, but they're very good at sensing. Like the coherence here is 10 milliseconds. So that's a long time. So again, for example, these companies are leading in the space and mainly for sensing applications rather than computing. Okay, so
Yes, just a question. So 10 days ago, North Quantic got another round of funding, valuation of 1.4 billion US in Where does their qubit architecture fits in?
Their Qubit is actually kind of a mix of kind of a photonic and a superconducting type system. And their claim to fame is that they need less physical qubits to manifest a logical qubit. So in all these systems I talked about, you need a lot of physical qubits to actually manifest a logical qubit. But with Nord Quantique, what their promise is again the ability to have less qubits for that. So their system is actually very interesting in terms of that.
Is there an advantage to having this physical?
Well, there's less things to correct.
Oh,
And less energy to maintain.
Possibly. Those are all, you know, the details get a little bit more problematic, but they're working.
NVIDIA is going into quantum. You have an idea of the technology they will follow?
Good question. No, I'm not really familiar with what they're going to go into. No. Good question. How much time do I have?
Don't worry, more very long time.
Okay, so now that we talk about the pretty picture, well, I went skydiving once, and when I went skydiving for the first time, in the morning they talk about everything going well. In the afternoon they talk about everything going wrong. Right. So now this is the afternoon, and we're going to talk about how things go wrong. Yeah. So there's a paper that just came out recently, and challenges and opportunities for information hardware. So these are the qubits that I talked about, that I introduced, and also their TRL level, the test readiness level. Right? Well, what are they good at? For example, quantum computing, you've got really the one that's, like I said, the superconducting is really out there for the TRL 6 technique. Trapped ions pretty close behind, but you can see how it's alive. And then quantum simulation, right? Looking at a molecule, how to simulate that molecule using quantum information, but now leaving the pack of neutral atoms, which makes sense. Quantum networking, of course, you're going to have your photonics right at the top there because they're the flying qubits that you need. And then quantum sensing, you'll have the spin defects, like I said before. So you can look at this and say, well, okay, those are the issues, and as a company, I can see, well, how can I improve this? What technology do I have when I look at these quantum types of information? What kind of technologies can I add to this to improve it? Right. So this is actually a very helpful picture to tell you where the problems are.
It's really interesting. So what's interesting here is that it demonstrates that actually the qubit modality relates to the particular applications.
Yes, exactly.
So it's not that all qubits are good for everything else.
Yes.
It just clearly shows how
Absolutely.
modality applicate, or how to say, modality determines.
Which goes back to my point where that's the classical world is I can make a system independent of the algorithm or the application and just use it, versus in the quantum world, no, the hardware, the software, and the application have to line up. Right. So that's a good point.
Sure. So does that mean that you are constructing, building architecting systems that are very specific in their intended outcomes?
Yeah.
Right. So you're designing systems that have direct applications, healthcare, finance, defense, and those systems would not necessarily be architected to go in a multimodal way across those different industries or
Exactly.
environments.
This is the non-classical thinking that we have to get. The classical thing we need to get away from, right?
So it's almost like a hyper local type
Yeah,
of structure.
it's new. So quantum is a force multiplier.
Yeah.
Right. It's when I say quantum technologies, it's about increasing the efficiency of a classical system. Right.
There's lots of people in the world that are struggling with the level of efficiency we already have.
Yeah, exactly. And so perhaps in this particular application, the quantum computer or the quantum technology can actually lower the efficiency.
Sure.
You're not breaking, P equal NP with a quantum computer. It's not, you're not getting to a new regime. Maybe we might get into a new regime of computation. Maybe with quantum, maybe with something else.
Mm-hmm.
But right now, the point is, how do we get an intractable classical problem to be actually tractable, to actually have a solution without having to wait for the age of the universe and get the answer. And these questions are very important. For example, decrypting. An important aspect here I want to make sure that I want to line up here is the material system is very, very important. So for example, looking at, very good materials to implement the system is critical. For example, silicon nitride, which I'm working on with Connor Kupchak here at Carleton, using their LPCVD system to implement silicon nitride. Because silicon nitride is very low loss material. It actually has a whole bunch of things that are very useful. It's non-linear, meaning that it can process light with light, and it's very low loss. And we can do things where we can play with the waveguides and make systems that are ready to connect to flying Qubit. Okay, I think this is probably the key takeaway of the talk. Okay, and this is where I was getting at. Quantum is like, oh, quantum, no, okay. But actually, the classical world is so important to realize in quantum. So classical technologies are the key to make quantum successful. Quantum advantages come from quantum physics, but quantum technologies are built, controlled, and scaled by classical technology. So if you're already working in the classical technology sphere, you don't really have to change much. It's looking at what can we control with the classical system? What kind of material systems can become that are usually for classical systems that we can improve or enrich for quantum systems? So for example, the essential foundations, ultra precise engineering, that's very important. Nanofabrication, high vacuum systems. How do we make them better? Cryogenic systems. How do we keep them colder longer? Advanced materials. What kind of materials are out there that can hold a qubit longer, or that can, very extremely low loss or very high nonlinearity, but yet low loss at the same time? One of the questions is I can access one important feature of the material, but not the other. I want to do that at the same time. Classical electronics, like I said, the FPGAs, very important for control systems. Control systems of making a rocket land back on its nozzle again. That's kind of the same what's needed in fault tolerance in quantum computing. Lasers and optics. A lot of these systems are manipulated and interrogated by lasers. High precision lasers, very important, very narrow light, getting precise information. Control and measurement, right? How do I do a measurement really fast, really quickly, and feed it down the system forward very quickly? Those are very challenging problems, even in classical technologies. And then classical computing. It's not just the quantum computer is not going to be replacing classical computing, right? So the classical computing needs to also catch up to what needs to do with how to interface to a quantum computer. All these things go into enabling the quantum system. Cryogenics, isolation, control signal, readout, classical feedback, all that is very critical. And what's out there already can be used and can be improved upon. And imagine that if you're improving upon it for classical means, for quantum means, and you can go and make your classical applications that much better. Right? It's just making classical better. Whether you're going to use it for quantum or not, that's the hope. And then these go and they're enabled by these awesome efficiency technologies are enabled by classical technology. Quantum computing, communication, sensing, simulation. So the connection is really classical technologies provide the tools, control, and stability. Stability is very important, and scalability, right? Then the quantum physics, it provides you the superposition, the entanglement, variance. That's all really the tip of the iceberg. The bottom of the iceberg really is the classical. And together they make the quantum. And so the key takeaway here is that quantum technologies don't replace classical systems. They depend on them. Okay? Classical excellence makes quantum advantage possible. So that's the message to the community. The classical stuff that you guys are working on already is key to making quantum come to life. Now the challenges. So this paper came out recently by John Preskill. He's one of the leading people in the field. He's actually responsible for a quantum algorithm, quantum state called GKP states that are being used by a lot of companies to manifest quantum biz. And he wrote this Mind the Gaps, the fraught road to quantum advantage. Okay. And in the introduction, basically, he says that quantum computing is advancing rapidly, yet substantial gaps separate today's noisy intermediate scale, noisy meaning that we're living with qubits that have noise, to tomorrow's fault-tolerant ones that actually eliminate the noise. We identify 4 related hurdles along the road: error mitigation to active error detection and correction, rudimentary error correction to scale fault tolerance, from early heuristics to mature verifiable algorithms, and from exploring simulators to credible advantages of quantum simulation. So you'll see now, actually, in the news, they're discovering new algorithms to help them with the hardware. And that's really the threat that's coming right now. Have you heard of Q-Day? Like Doomsday, Q-Day is where all of a sudden everyone can decrypt your information, right? And they're saying now it's 2029 or 2030, because these algorithms are getting out of hand. The science, the computer science, Professor Barbeau, that stuff there is so important, and it's actually accelerating the threat. And so, for example, quantum safe, all that thing, take it seriously. The quantum hardware platform. So these are some of the little highlights that he has in the paper. There, quantum hardware platforms are advancing steadily, but no one knows when computer will run applications that are broadly beneficial. So we don't know yet, right? I have better algorithms, but I don't know. 2029, 2030, I don't know what's going to happen. The path from noisy to fault tolerance is likely to be arduous, expensive, and prolonged. We seek applications that are quantumly easy, classically hard, and hard. Okay, like ours. An error-corrected quantum machine will actually, this is important here, again, this is the take-home. An error-corrected quantum machine will actually be a hybrid system requiring substantial classical processing power to decode error signals. Substantial. Okay. And we don't know yet which quantum computing modalities will be best suited for scaling to large systems that solve hard problems. But these are some of the open questions that people are working very hard on right now to solve. But fear not, NRC is on top of this. So we support the national strategy, funding, de-risking, and creating supportive policy frameworks for emerging technologies, defeating and coordinating, procuring goods and services, and serving as a research partner. So we have the mechanisms to support the ecosystem to try to tackle these problems. And then we have hopefully more funding to do this. And also the DISC strategy, the defense industrial strategy, is also very keen on solving these problems. So NRC and this is very interested to solve these problems. So NRC supports all Canadian strategies. So the portfolios here, we have a whole bunch of challenge programs to address these issues, with the new one that recently came out with the quantum networking, the applied quantum computing, the quantum sensors. And then we have these things called small teams and ideation projects that look at smaller problems. We have the research centers really that are interested in getting to the bottom of these things. The extreme photonics is very important for control systems. It's very fast lasers. Digital technologies are really looking at the algorithm part of things. And metrology is the measurement. And then the quantum nanotechnology research, which I'm part of, is really for engineering and material system development. And then we have the CPFC logo. And then we have the IRAP program to help the community and the ecosystem grow and give them the tools that they need to succeed. So we're bringing expertise to collaborations from photonics, electronics, metrology, right to the quantum networking that we're trying to get memories, repeaters. And then we have, we're working with the different players in this field and working with them with our own research scientists to get to the bottom of these very daunting challenges. So from that paper, despite our best efforts to predict the important application, tomorrow's quantum computers are sure to delight and benefit us in ways we cannot currently appreciate. Before that happens, we have a lot of work. And with that, I thank you.
Okay, let's start with the questions. I already have one.
Mm.
So, given this discrepancy between the logical qubit and the physical qubit, the logical qubit is the qubit used in the calculator, one that you really works out the algorithm, and the physical qubits are the one that support the logical qubit to do their job. So, given that some people say that the ratio is 1 to 1,000 or 1 to 500, you need 500-ish physical to keep one logical. Let's use it as a reference. Can we really hope that one day we'll have something that looks like a computer, or the real hope is for a cloud solution that somewhere in a warehouse there is something called computer, but it's actually so big that it's hard to imagine it as a computer?
Well, from what I see right now, it almost looks like a cloud answer, right? You've got your quantum system because it needs, for example, the superconducting system needs temperatures that are very, very low in temperature. So it's hard to have, millikelvins on your desk. So that's not something that's easy to do. So you would think that the system itself that's doing the processing would be, in the cloud, and you would access it that way. But again, we have to see that quantum computing isn't going to be replacing classical computing. It's going to be part or accelerating what a classical computer can do. So for the foreseeable future, what I see is that you'll be connected to the cloud. You're not going to, maybe as they scale with atomic systems, and you can make that, like, for example, modulating. The cryogenic systems are getting better. They're getting smaller and more modular, portable. But I think if anything were to happen, it would probably be accessing the quantum computer from the cloud. And you can actually do that now with IBM. They have a little cheap card trick that you can access that actually accesses the quantum computers and show you how you can pick out the queen faster than anything else.
Yeah. Thank you. Questions?
Can you say a few words about what is happening in Southeast Asia, about the technologies they are adopting, and where they are with respect to, I think most of the technologies you mentioned, they are Europeans or American or Canadian. But what about what is happening in Southeast Asia?
As far as I know, these are the kind of the modalities are being used everywhere.
Mhm.
I'm not aware of any other modality outside of what we're talking about here. I'm not sure actually what they're looking at, but I think it's very similar. Like we heard in the news that China, for example, are able to teleport photons to space, and it's usually using very similar type generation of single photons. So, but modalities are right now the leading modality is the superconducting qubit. So people would be looking at that. It's just that the tools needed to get the other ones to compete are just not there yet. And this is where perhaps classical technologies can win out in the material systems. So that's as much as I know of that.
Yeah, another question. Control. So you talk about a lot about control and how important it is for quantum computing. So one of the aspects is controlling the generation of single photons. So it's important for photonic-based quantum computing.
Yes,
Also
absolutely.
for quantum communication. So I know it's a hard problem, but where are we right now with the our ability to control the generation of single photons?
We're actually, again, we are pretty close. The issue here is, again, it comes down to sort of electronic control. If you're generating a single photon, you're generating a single photon from some type of electronic recombination situation. And what happens is that you're generating in an environment that is either probabilistic. Like if you look at some of the crystals that generate single photons, they do it in a very probabilistic way. So I don't know when that photon is going to come up, but it comes up. We don't want to be there. We want to be in a deterministic situation. So to be a deterministic situation, you need to have a semiconductor environment. Okay. But in the semiconductor environment, you have situations that are kind of fluctuating. And that creates some type of another probabilistic thing overlay on the deterministic system that you're trying to create. So they're getting better in terms of purification of the materials. They're getting better in terms of creating the cavities that are required. There's still drift going on and things like that they need to solve. So, what's the typical answer? 5 years, whatever, but that's what they're dealing with right now. And it's really just the traditional, traps, noise traps, charge traps that even traditional electronics plays with. So what's plaguing electronics to get better is also plaguing the quantum system. So this is where the push is that you keep focusing on the classical systems, keep focusing on the material engineering. And it's going to be very useful for quantum, but it's also going to be very useful for classical.
Question online, someone is asking, is there a Qubit modality that fits best quantum safe context?
The way I understand quantum safe is that you're actually using classical algorithms to protect yourself against a quantum attack or a quantum trying to break your system through a quantum computer. So quantum safe is really just a way of saying this is a classical algorithm that protects you against a quantum computer. So there is no modality per se for, the modality is the transistor. So the quantum safe is not an actual quantum hardware software application. It's a shield. It's a classical shield against quantum that may or may not hold up.
Yeah. Another thing that you were relating, you were saying that we have in a qubit there are multiple states, potential paths that could be influenced in a way that you can increase the probability for one outcome or the other. This influencing is through the quantum gates, right? It is the quantum gates that manipulate the interference so that we could potentially measure something that may be affected by this, right?
Yeah, it's the arrangement of the actual system, right? The quantum circuit itself is arranged in such a way to address that particular problem. And that's why I keep saying that quantum, when it comes to hardware and software, they're tied at the hip. When you have a particular software application you need to solve, the quantum hardware needs to follow. In the classical system, I just make a computer and I make a program and I run it on any old computer.
Actually, the processor is algorithmically defined.
Yes, absolutely. Yeah, that sounds good. Yeah,
Yeah.
sounds good. That's it. It's algorithmically defined, exactly. Because you need to account for creating the phase and then playing with the phase information. Like I said, the Van Bont tester, the photon's reacting to something that it shouldn't react to. It has knowledge of something that it shouldn't have knowledge to. And that knowledge comes to the phase of the wave function. That's real. That there's something there that's informing it or changing its actions or changing its dynamics because of phase relationship. So that's what we're exploiting right now. Is that how do we control those phase relationships to get access to counterfactualities that would speed things up? Not necessarily to bring us something new, but speed things up.
Yep. That has pretty remarkable commercial applications. So we start thinking about the algorithm being boutique. It's a product design.
Yeah.
Yeah. Right. Because you can dial in whatever specific set of values you have, whether they even be national in structure, and then that can be projected in a sense as a product wrapper. So can you talk a little bit about some of the commercialization aspects of quantum as they exist at the present time. Like I understand quantum sensing as it relates to natural resources. I understand the cryptographic elements of harvest now, decrypt later, and the protections that go in, but maybe expand on the financial services applications, being able to broaden out equality, right, distribution systems that actually benefit society. Because a lot of what I'm seeing with a lot of these technologies is they're very abstract in a sense, right? Like, there's an acceleration, yes, but we're contending with large numbers of people that are already struggling with adoption curves. And, you know, so with my background is portfolio management, it's investment management, building at scale. So I can wrap my head around these systems, and I did a lot of investing in convergence technologies. But like, we're talking about the acceleration of solutions, right? Because we're building this for solutions.
Yes.
Okay, to risks, you know, that people maybe don't fully grasp the severity of at the moment. So just maybe expand on commercial applications, particularly in finance or like benefit society.
Actually, funny.
Because I think we need to shift the narrative a little bit. Like there's a lot of people that are kind of getting against AI, against quantum, and that's not good because other jurisdictions are developing and we're just going to be at risk.
Yes, yes, absolutely. Yeah, and to your point there, if you go to any quantum conference, you'll see a lot of banks supporting those conferences.
Yep.
So they're very interested in using algorithms to sort of predict market behavior.
Sure.
So if you think of the world as made out of quantum, and if I can hack the universe's computer with quantum information, then I have an edge in terms of predicting what's going to happen.
Right.
So, for example, quantum simulation usually is in looking at solutions for cancer or drug discovery.
Right.
But they're also looking at behavior of human beings in the market. And here's actually a very cool paper that you might be wanting to read. It's an experiment that they found correlation among an internet game across the whole world. And they used quantum entanglement to talk about so something called the Bell inequality. And they ran this experiment to show that people's answers to these games are correlated. So there's a pattern in how people act. And the quantum experiment discovered that, pulled it out. So you can almost see the potentiality here. The only issue stopping us making this real is the engineering. It's the actual boots on the ground, getting this going. And so we know the math. We know what needs to do. The algorithms are there. We just need the engineering. We need the resources, the actual bridge build. So these are very cool. They're very, but that's what's stopping us now. The actual effort of engineering.
Because we haven't been able to actually productize this.
Well, the thing is that you see that for the first quantum computing company was D-Wave, right? And they took a very simple quantum aspect of things. So, for example, in quantum systems, there's always a search for the ground state, right? And if the lowest energy state, right? If you realize that lowest energy state to be some perfect path for trucking systems to take, and you realize those things, the system will actually come down and try to calculate or get to a lower state, and you can extract that information to whatever model that you want. Okay. So that was adopted quite quickly. It was Canada's first quantum computing company. And systems were kind of broke into the market, right? And now companies like Xanadu and Photonic, they're also breaking into that market and looking with and partnering with established companies like banks as well, banks and Rolls-Royce, things like that. It's all public information in terms of who they're partnering with. So they're working with businesses and trying to tailor what the businesses need.
Yeah, that's clear. I mean, it's $200 million RBC to Photonic on May 14th, right? So, okay, so I don't want to monopolize time, but I would just ask around, let's say from a asset allocation perspective, like being able to efficiently allocate money for the betterment of a society or an individual or a company. Okay, what is the barrier in the engineering and the technology that exists today to not be able to map that in this precise, elegant quantum way? Like, what's the physical barrier?
Yeah, so the algorithms are there. We know what we need to do. The physical barrier is actually the fault tolerance. Right. right? The error.
So it's still unreliable as a
Exactly.
technology that can be implemented at scale within a financial.
Exactly, and that's exactly what I was talking about, the fraught road to quantum advantage, is that the issue here is the fault tolerance of it. The systems, like I said, you're balancing a pencil on its head.
Yeah.
And that's why control systems are so important. That's why now the electronics, FPGAs, all the traditional electronic stuff is coming into the controlling system. So that's actually key, and we're getting closer and closer to that. So can we work with, and this is why the algorithm mode is so important. Okay, it's hard to manage all these physical qubits. Can we reduce the number of physical qubits by changing our algorithms? And that's where the threat is coming up. Whereas we make the algorithms more efficient, we don't need so many resources. So it's called resource estimation. How do we estimate the resources needed? These are all open questions in computational complexity. These are actually, this is theoretical quantum.
What you're saying is the probabilities are narrowing.
Absolutely, absolutely. So it's almost like the classical world was a disconnect between the software people and the hardware people. As a I know this in my own field. As a hardware person, I want to make the best resonator I can. And I'm going to work really hard, and I'm not going to tell people it's ready yet because it's not to my liking. However, the computer scientist said, you don't need to make it that good. I can do something that, so they're starting to do that. They're starting to talk.
At the application level.
Exactly. But before, it's like, I need to make the best transistor in the world. Right? And that world, yeah, okay, fine, sure, it makes things better. But what happens is this mindset is I need to be the best in my particular field right now. But the algorithm doesn't need your best. It just needs this. And they're starting to talk now. So that's where you see the acceleration.
Yeah, especially with a lot of the recursive systems that they have right now.
Yeah, so there were some other questions referring to the major barriers, but you already addressed some of those in the discussion was this. So, Babatunde, I think you found the answers. Also, we'll share the articles of Preskill and
Yes.
and the others where they in the challenges where they go in detail. So think about other questions just to make one point before people start slowly disappearing. So we will share the slides and we'll share the video. If you look for a link, remember a couple of words: Carleton, Sprott, tin, quantum. If you write those words together, or at least 3 of them, you'll get to the website of the seminar. And every seminar, there'll be a link provided with the materials that could be shared after that. This is one point. The second point is that just to let people know, June is coming. We were planning to have a seminar in June, but it's a very busy month, a lot of conferences, and we're pushing it a little bit. So we decided for the next seminar to be in September. We already have a speaker, Madhavi Mantha. She's online. Thank you for joining. She's from the so-called PINC organization, which is, as far as I can pronounce it, it's a Plateforme d'Innovation Numérique et Quantique, a digital and quantum innovation platform. It's a not-for-profit organization that really helping organizations to adopt quantum technologies, working in many different domains, including finance and others. Madhavi agreed, and she'll be talking about what they do and the challenges people need to adopt. They already have implemented the IBM access to the IBM cloud services and really work with companies that would actually benefit helping. So this was just a small point. Other questions?
Sorry?
Yes. If you want to say a few words. Okay. Yeah. So are there any other questions?
We were having this conversation outside, but like just to clarify, because you mentioned it right now too, like the software and the hardware need to communicate and talk better and have like, we need to create systems where those two can like work together better. What does that look like in practice? And what were the initial, like in the classical way of thinking, what were some of the blockers and how is that evolving or changing to support the way of quantum?
So your first question is what does that look like?
Yeah.
Yeah, so like I was saying, for example, when you're working on the hardware, you're working on a particular objective. You're trying to get the hardware to do what you do. And the software is also doing what it needs to do. But when they talk to each other, they realize that they can get to something faster and more useful without actually having to perfect everything that they need to do, right? And that's something where you have, and it's coming together now. You see more of the algorithm people talking with the hardware, working together side by side with them. In quantum companies, that's actually essential, right? Because it's the particular algorithm that you're realizing in hardware. And so that is what that's what that looks like, I guess, in the sense that if you look at schools, for example, schools should have, like in nanotechnology, when people start studying nanotechnology, they study a little bit of chemistry, there's still a little bit of this. In the quantum sciences, they should start now looking at algorithm design for the hardware first, or hardware design for the algorithm first, right? That's important to start to actually cross boundaries in control systems for algorithm, right? And so that's actually something that should be, and it is being looked at more in universities that are training the talent for that. So as nanotechnology brought the fields together, quantum technologies will bring the software and hardware together. Hope that helps.
Yes, thank you.
Okay, so, yeah, so one just educational thing about the coherence time, which seems to be a key parameter.
Yes.
Right?
Yeah.
So this is what actually keeps the qubit be what it is.
Coherence,
Right?
yes, yes.
You know, the time when the superposition, you know. Yeah, another question. So you never mentioned entanglement. So entanglement seems to be a higher order interaction, you know.
Yes.
You don't necessarily need entanglement for a quantum computer to work. Is this correct statement?
No, you do, because now you can think of entanglement as a higher order superposition, right? So now as you, what happens now, like for example, in the RSA example, okay, you have a bunch of superpositions that are across a large qubit number, okay, that represent the digit of the composite number that you're trying to break, okay? Now, in quantum encryption, what you're trying to do is you're trying to find things called remainders of division. So you have your system that represents the numbers, you do your division, but you need to keep the remainder in another qubit bunch. That remainder qubits, the remainder qubits are entangled with the actual number qubits, right? And then what is happening is there's some mathematical magic. What ends up happening is you start seeing a period in the remainders. There's a periodic behavior in the remainders. So that if I select just one remainder, if I select that particular remainder, I get all those numbers that are separated from each other. And then I feed it into something called a quantum Fourier transform, and I get the remainder number, the exponential number of what you get, to start to factor something a lot faster. So the entanglement is actually very important because you're trying to do measurement on one and not the other. And then if you measure one, you collapse. You get rid of other things that you don't want, but you have the stream that you want. So entanglement is actually a very important aspect to quantum computing.
Yeah, but still looking at it as a kind of a higher order.
It's a higher order position.
Let me then. So are they qubits that are harder to entangle?
Are there qubits that are harder to entangle? Any type of conservation rule that occurs between two qubits, you get them entangled. So, for example, photons get entangled when they go through a beam splitter. You don't know which way it's going to go. As long as you create ignorance in that system. Now, the details, you know, it's hard to get a photon to interact with another photon at exactly that moment. That's why quantum memories are important. When you have a quantum memory, you can hold on to that photon. The other one takes a little bit of time. It gets there, you hold it, you let it go, and then it hits at the same time. That's entanglement between photons. Entanglement between holes and transmons. Yes, you got to wait for you got to make certain measurements, or you got to have certain circuitry that will be ambiguous. So each one, it really is the detail of how you actually engineer it, which makes it hard or not hard. Right? But from a fundamental perspective, like fundamentally physics, no, they're all, you can entanglement is quite easy. But to implement it in a hardware perspective, it may be harder to do it in this system than in that system. Maybe trapped ions are harder to do it than neutral ions.
Okay, well, if there are no other questions, I would like to thank you, Khaled.
Thank you very much.
Again, we're looking forward to our future events. I'm sure that we'll have other opportunities to listen to Khaled and other people from NRC. As I said, our next seminar is planned for September 29th, when that in a month we'll be talking about partnership, potential project, real engagements with quantum technologies and examples and so on and so on. But thank you very much to everyone. It was another good session. Keep tuned on we'll follow up with the slides and the recording and everything. Okay, all the best.